So I will talk about a strategic project that we have, and I thought it's appropriate because I was told that you have quite different backgrounds, and so I don't want to be too technical, but just convey the way we are thinking. And this is work in collaboration with Ayub Aruna and Mohamed Gunes, who were both PhD students on the project, and Matteo Gatti is my permanent colleague in Paris. And we really benefited from collaborations in the group and outside the group, and in particular with Xian Shen and with Xu. So our group aims to, as the name theoretical spectroscopy group says, aims to predict, interpret, analyze, understand spectroscopic features. And we span the way from fundamental theory development that we need for this purpose up to collaboration with experimentalists and also with applications, sometimes with industry. And this can be optoelectronics. We have a lot of collaboration on photovoltaics. And so we have to look also into materials. So today, I will briefly put ourselves all on the same footing, talking about functionals that are things that we don't know. And then set the philosophy of our project, which we call work once, store and share. And this is like, as you will see, like playing Lego. And then we will have examples, development of a new functional for the exchange correlation potential in Kohn-Sham density functional theory, and also a functional for the charge density as a functional of the potential. And then we can look at further aspects if there's time. So functionals, well, the purpose of all of us, I guess, is to calculate observables. And in a many-body system at temperature 0, we would just express these observables as expectation values of some operator that characterizes the observable and the many-body wave function. And this is, of course, a very simple expression. And we say that the observable is a functional of the many-body wave function just because this is an integral where the many-body wave function appears. So when you have the many-body wave function and you know your operator, you get your observable. It's a well-known expression. So in this sense, we are not theorists, right? We are not inventing new theory. We have our expressions. And the only problem is that, of course, computationally, this is not possible. And so what we will do is to rewrite the project, the problem, such that we can actually access approximately our observables. So if you think about it, the many-body wave function is an exceedingly complex object, depending on many, many variables. But the information about the system is much easier. The information about the system in the Hamiltonian is encoded in the external potential. Once you think that you know what is a kinetic energy operator, you think that you know the Coulomb interaction, then there's only the external potential that characterizes your system, and it carries all the information. And that means that the information can be much more compact than the information in the many-body wave function. And this actually means that the observable, instead of expressing it as a functional of the many-body wave function, you should also be able to express it as a functional of the external potential. And this means that now you have a descriptor, let's call it a descriptor, that is much more compact than the many-body wave function, right? And of course, in principle, you know this expression. For example, if you are at finite temperature, you can just write it as a trace, and the external potential is in the Hamiltonian. So it's an explicit expression, but again, it's very, very complex. So now the information is actually in this simple function, the external potential, but the expression is very complicated. Whereas before we had a simple expression, just an integral of a very complicated object. And this brings you to the idea to say, well, we have these two possibilities, but in between, could we actually encode the information in still another object, a reasonably compact, simple object, which I call Q, and have an expression, the observable, as a functional of this object that is again treatable. Okay, so we need an object Q that carries the information about the system, or at least enough information for the observable we are interested in, and then an expression that we can handle. And this Q can itself be an observable. And we should not forget, we are rewriting, but not because we think that in this way we can solve the problem exactly. We will never be able to solve this problem exactly. We are heading for a way to find efficient approximations. So now it could be that, first of all, it's not so easy to find this object Q, and then we have to find the expression for the observable as a functional of this Q. And let's just be a little bit more precise. Let's take density functional theory, which is probably the example in the case. So in density functional theory, the descriptor, so the object that carries the information, it's very compact, is the charge density, the function of a single three-dimensional space variable. Okay, and you don't know the charge density from the start. So you have a first problem to get the charge density. Okay, and what we do in density functional theory often is we build an auxiliary system. So we build a set of equations, the Kohn-Sham equations, that are simpler than the many-body problem, but they are only designed to give you this object, the charge density. Any other information that this equation will give you will not be correct. Okay, it's an auxiliary system. And this auxiliary system has an auxiliary potential, which is the exchange, which contains an exchange correlation component, with its the Kohn-Sham exchange correlation potential that we consider to be itself a functional of the density. Okay, so suppose that you have a good approximation for this auxiliary potential, which is a problem per se, as we will see. Then you have the density, and then you have to build your observables as functionals of the density, which is again difficult. So in density functional theory, historically, most people try to find the total energy as a functional of the density. This is also because the total energy is variational, but it's also a historical problem. And so the total energy as a functional of the density is not known exactly, and people have spent decades, hundreds of people spent decades to get better and better functional for this one observable. And most observables are not easy to express in terms of the density. We don't know them. Actually, we have no clue about most observables. And that, therefore, many people in the density functional business replace the observables that we are supposed to calculate by the observables calculated in the Kohn-Sham system. So sort of auxiliary observables. And of course, they are not correct, right? So the most famous example is the band gap. If you take the eigenvalues of the Kohn-Sham equation and you take the band gap, this is usually much too small. And this is because, not because you did an approximation on the exchange correlation potential, we will also see this, but because intrinsically, Kohn-Sham system is an auxiliary system not meant to give you anything else but the charge density. Okay? But we have other possibilities. So when you are stuck there and you say, oh God, I don't know how to express my observable as a function of the density, then you go back and say, but I have other possibilities. In between the very compact charge density and the very complex many-body wave function, there are other possibilities. And one possibility is, for example, the one-body Green's function. So the one-body Green's function, which depends on two space objects, arguments, actually also two spins, and a frequency. This is a very good object because if you take its diagonal in reciprocal space and the imaginary part, you get the spectral function that is very much linked to photo emission experiments. So this is an observable that you can immediately get from the one-body Green's function. You also know in the Galitzky-Migdal formalism how to express the total energy in terms of the one-body Green's function. You have an exact expression. But there are other things you don't know. For example, the dielectric function. You don't know exactly how to express the dielectric function in terms of the one-body Green's function, but you have more observables. Price to pay, of course, this object is more complicated than the one-body charge density. And again, you have to find it. And in order to find it, you will have something like an auxiliary system. And this auxiliary system will have something like an interacting potential, an effective potential. And in this case, it's the self-energy. which is, of course, more complicated than the Coulomb potential because it has to give you a more complicated object. So self-energy itself, a function of 2 space and 2 spin argument and 1 frequency, and we consider it usually to be a functional of the one-body Green's function. And then we have to approximate this self-energy. And there are other possibilities. You can be interested in the orbital local, so the orbital projected local part of the one-body Green's function. And then you have to build another auxiliary system with a local self-energy, which you have to find somehow, and which people here who are doing DMFT, of course, would immediately recognize. And from this local Green's function, you can go get local observables, in principle exactly like the local spectral function, whereas if you want to have the K-resolved spectral function, you will have to resort to approximations. And again, you have to find your local self-energy to get this one-body Green's function. And you can push this further and further. Actually, you can have many different descriptors, like the one-body reduced density matrix, or even other things, spectral density. And for in each case, you have to build your corresponding auxiliary systems, and you will get certain observables in principle very easily and others not. And if you're interested, we also have a sort of general discussion on this. But a common thing here is that we do not know exactly any of these auxiliary potentials, auxiliary interactions, and etc. So we have to approximate our auxiliary system. And often we don't know the observable exactly as a functional of this descriptor. So we have 2 problems. Okay, so how shall we go about it? So we have this double complexity, which we should not forget. We have a complexity because we have interaction. So we have many-body problem. And we have a complexity, especially in our group, because we're interested in real problems, photovoltaics, optical data storage. Real materials are per se really complex, and the 2 things are intertwined. And this means that when we do computations, we do huge computations from scratch, which is an ecological problem, as we know today. And it's also a problem for understanding, because when you mix all these complexities and you don't want to do just number crunching at the end, how do you analyze? And of course, the idea would be if we could extract universal pieces. So this is the strategy that we call work once, meaning calculating universal pieces that are not just, for example, the Coulomb interaction, but a sort of effect of the Coulomb interaction. Store these pieces, interpolate these pieces, and make them available such that we don't have to recalculate them every time. This is our long-term ambition. Okay, and this is like when you play Lego. So when I was a child, we were playing with these small Lego pieces, and this is like solving the many-body Schrödinger equation, right? You have all these small pieces, and you put them together, very complicated. And today, if you go to a Lego shop, you will find these prefabricated pieces, wheels, shovels, and so on and so on. And then you can build your complex object out of these pieces. And we have sort of the same problem in our many-body physics. If you look at a photoemission spectrum, like this one is a photoemission of aluminum, you will recognize the band structure up there, band structure. Then you have satellites and other satellites. And if you look at the photoemission spectrum of different materials, they all look then similar. They have a sort of global structure. And so you would like to put together these pieces and not recalculate every time from scratch everything. So they would be faster. You want to calculate less, and it helps you to understand, because you understand these pieces and then the way you bring them together. This actually is already done. So let's again go back to density functional theory. I know that most of you are not density functional people, but it's still a very interesting approach, gives you a lot of insight. So in density functional theory, you have to find this exchange correlation potential as a functional of the density. And when density functional theory was written down, no one had a clue of how this potential would look like. In fact, I learned density functional theory at university. We had 1 hour on this in the solid state course, and the professor said, I have to teach you this. They told me to teach you this. It's completely useless, but I will do it, okay? This was my introduction to DFT. Yeah, because we don't know. So what shall we do? But Kohn and Shum had this very clever idea right from the beginning. And this is to say, it's based on the idea of nearsightedness of Walter Kohn. When you are in a complex material at some point, and you want to know certain information, for example, this exchange correlation potential in that point, it will essentially depend on what's going on here. So in this case, on the charge density just here. And this means that you can take the charge density just here and replace the rest of the charge density by just a homogeneous value of this local value. So you take, instead of taking the exchange correlation potential that depends on the density everywhere, which is different everywhere, you take the exchange correlation potential of a homogeneous system with a charge density that is actually the local density. Okay, this is the famous local density approximation. And this has enabled the calculation and DFT actually to fly, right? So you need this exchange correlation potential only in a homogeneous system. Nearsightedness is really the concept here. And if you think about it, when you do single-site DMFT, you do something really similar. So you're interested in the local self-energy, and you have the orbital local one-body Green's function. And you will take the local self-energy in the real material from a model, which in this case is the Anderson impurity model. It's not the homogeneous electron gas, but it's still a model. And this Anderson impurity model will be the model that has the same local one-body Green's function or spectral function as you have in your real material. So you again have this self-consistency. And again, you have this idea of complete nearsightedness. It's a very winning strategy. So you do very, very similar thing, actually. So the strategy to take information from a model and to suppose nearsightedness is a very powerful strategy that you will find in different contexts. There is something more about what you do in the local density approximation. And I think it's actually this thing that has allowed DFT to have the success that it had from the very beginning. Otherwise, it would have been forgotten. And this is that people were able to calculate the homogeneous electron gas and to store the result. And this is in particular the work of Sepperly and Alder. So they calculated for different densities the exchange correlation energy per particle or the exchange correlation potential. And then this was interpolated and was made available. And we still use it today. So one really big calculation, quantum Monte Carlo. And this allows us, when we say density functional theory calculations are efficient, they're actually only efficient because the hard part has been done for us. And it has been done for us once and forever, right? We do not every time go back and calculate these exchange correlation effects. That's actually a difference to dynamical mean field theory, where people solve the Anderson impurity model over and over again, and probably also in this case one day, I hope someone will be able to tabulate and share the results. So this is actually the realization, this local density approximation is the realization of the work one, store and share strategy that is our inspiration. So we want to learn from this and related approaches, and we want to go beyond. So we want to go beyond nearsightedness because we know that, of course, this is a rough approximation. It's very powerful, but it's not sufficient. We want to have models that are not a homogeneous electron gas. And also we want to apply this strategy to cases that are not density functional theory. Okay. I will, however, talk about density functional theory today just because it's easier. And so I will talk about the exchange correlation potential as a functional of the density. And then if I have time, about the charge density as a functional of the external potential. Okay, so we are looking for an approach where you can have building blocks that you can calculate once and forever and you can store. And the simplest example is a Taylor expansion. If you Taylor expand, you have a function f of x and you expand around some point and you think that you know the function here can be a function of one variable of a vector of functional, right? And first order and so on. So you have to know the first derivative and so on. So you know a certain number of terms. You can get them once and forever, and then you can construct your function in any point X. That's the simplest example of what you can do. And this is perturbation theory. I come from many-body perturbation theory, right? So many-body perturbation theory is this. You have your self-energy that you don't know, and then you do perturbation theory, and you expand in the interaction, roughly speaking. So the first term is 0 because this potential only exists because there is interaction. And then you have the first derivative, which will give you Hartree-Fock and so on, okay? So now the problem of many-body perturbation theory, although I have done this all my life, is that you expand in the Coulomb interaction, which is universal. And this means that the terms, the 0 order, okay, this is 0, but let's say the first derivative, and so on, higher derivatives, are things that are not universal in the sense that they depend on the system. For example, it would contain the one-body Green's function. So for every material, we have to calculate these terms. So it does not at all fit our strategy because we don't have these building blocks that we can calculate once and forever. So many-body perturbation theory, besides many other problems that it has, like convergence problems and so on, also has the problem that it forces you to recalculate things over and over again. And this is actually what we think one should avoid, especially today. So if you don't want this, then you see you should not expand in the universal quantity. You should just expand in a system-specific quantity, such that the building blocks that you have are universal, okay? And the system-specific things are your descriptor, could be the external potential, it could be the density, the descriptors we have just been talking about. So for example, you could take your exchange correlation potential and you could expand it around some density that where you can calculate it. For example, a homogeneous density. We have just seen that this has been calculated by Zeppelin-Alder. And then you have a first derivative, okay? This is the so-called exchange correlation kernel. That is the first derivative with respect to the density of the exchange correlation potential. This is also known, it has been calculated by Moroni, Zeppeli, and Senatore, and it has been interpolated by Corradini and co-workers. So it's again a building block that we have, okay? And so this is the most logical expansion that you can do to meet this aim. Of course, we are not the first one to think that one could do an expansion. It's also not the first one we do it ourselves. We have even been done it in the last century. But this has never been done in a really systematic way. It was also very empirical always and not systematic and has been abandoned, but now we're taking this up again, okay? So we have these building blocks, it really fits our strategy. There is one big issue here that we have in materials, and this makes a little deviation here, and this is we need benchmarks. We should not underestimate this problem. When you are developing new theory, new functionals, new whatsoever, and you only compare to experiments, this is very complex. For example, you have a photo emission experiment, and you think that you measure the spectral function, but you don't measure the spectral function. You measure the spectral function, the surface, the electron, the photoelectron going out, scattering a lot of times, going to the detector, and at the end, you don't really have a benchmark. Then there are benchmarks for atoms, small molecules, small Hubbard systems. We really have benchmarks, but that's not enough when you're interested in materials. And so the benchmark problem is a big problem for us. And we are very grateful for this collaboration with Shiwei and his collaborators to get what we need, namely the charge density, a very reliable charge density calculated with auxiliary field Monte Carlo in real materials. And this one, for example, is bulk silicon that has been calculated in 21. And when we have the charge density, actually we can invert the Kohn-Sham problem, and this was the work of Ayub. If you have a reliable charge density, you can invert the Kohn-Sham problem with different algorithms. We used a very simple one here, an iterative algorithm, and get the exchange correlation potential that corresponds to that charge density. So in principle, the charge density is numerically exact. Your exchange correlation potential should be numerically exact. And in this way, actually, we managed to have the first really, in principle, numerically exact exchange correlation potential for a real solid. So how can you visualize this? The exchange correlation potential depends on the density everywhere. Okay, so it's a very complicated thing to visualize. But what we do is we plot it as a function of the local density. So in every point R in your material, you look at the density, you look at your exchange correlation potential, and you put a dot on this graph. If you are in the local density approximation, then VXC only depends on the local density, and this is simply a function. And it's a universal function, right? If you go beyond this, for example, you do a PBE, another functional, which contains gradients of the density, then this is not a local function anymore. And for every point R, you put a dot, and you will find that at some, for some densities, for example, you can have the same density in different regions in your material where you have a different environment, and therefore you get a different exchange correlation potential. So the deviation from this one single function tells you how much we need the fact that this is a functional of the density everywhere, right? And by the way, if you're curious, this color code here is the gradient of the density. So you can see that when you deviate from the curve, you have quite special environments. And of course, could do the same with the QMC. So we inverted the problem, calculated VXC from the QMC, and get the exchange correlation potential that corresponds to its charge density. It's down here. These are two curves. So we have the PBE and we have the QMC. And in one case, the color code is the gradient of the density, and in one case is the kinetic energy density. But that's just for analysis. Anyway, the result is, of course, the same. And so you can see also the QMC is not just a function, it has a little bit of noise, and also it has an extra branch here. The extra branch actually doesn't go in the same direction as the PBE extra branch. So you can already see that the PBE potential is not perfect, if we believe the QMC, which we do, of course.
Lucia,
I
just want to make sure
X of n everywhere.
So what you would present here is that for a given value of n of r, taken at some point, right? This is the range of that.
Exactly. Yeah. So in practice, you go to every point in your space. At every point, you measure the density and the exchange correlation potential. You look it up. Okay. You have the density and VXC of R. And this gives you a couple, density VXC, which allows you to put one dot on this graph. Okay. In the LDA, you will have a function if you do this. But now let's take again this example here. Let's say you have a complicated material, and in a complicated material, you can find in two different places the same density. Okay, of course. We have oscillations and so on. So let's say you have two different places with the same density. If your functional depends only on the local density, the value of VXC will be the same in these two places. But if your true functional also depends on what happens, for example, in the neighborhood, since the neighborhood is not the same, the value of VXC will not be the same. And this means that for the same density, you will have two different values of VXC. And this shows you how much this is a functional of the density everywhere and not just a simple function.
But I also want to know how to see it like a prime.
Absolutely. So exactly. So we do this for every point in space. For every point in space, here you find a dot.
No. What he's asking is a plot of n of r dxd of r plus some delta. You want to know that, and you're not telling him that at the moment. I mean,
So you want to know the functional at the end.
Well, that's what we want
Exactly, exactly. But if I tell you no, the seminar is too short. You understand? Yeah. No. This is this gives you an idea of non-locality. Okay, of what is how much we deviate from the LDA, but of course it doesn't tell you yet what we have to do. This is clear.
Okay. But I'm sorry, may I?
Yeah.
May I ask the question again about sort of the meaning and status of this thing? So, over how many materials was this constructed?
Okay.
And
so,
you know, because this looks like a very wide range of density.
Exactly. So this is one material. And I will make a side remark. I mean, of course, people who try to do machine learning for functionals, and in materials, they have the advantage, okay, they have the disadvantage that we don't have so much data, but the advantage that in one and the same material, you can have different environments. So you can still learn something. So here we looked at this one material.
Which one?
This is silicon. I'm sorry, I should have said it. I think I said it earlier. And then we will look at different materials, okay? But
silicon has densities ranging from, you know, essentially 0 in some units up to.
Yes, exactly. Because we would think that silicon is very homogeneous. For example, if you look at the distribution of eigenvalues, except for the gap, it's very plane wave-like. Yeah. But the density is not, it's a covalent material. You have to localize covalent bonds, right? Mm-hmm. Okay.
Can I ask a question here?
Sure.
This is a really interesting analysis. Just by looking at these two bottom plots, it seems as if this is saying that kind of giving support for a meta GGA, like this extra branch.
Absolutely. It does. Absolutely. Yeah. Had we seen this earlier, maybe we would have done the meta GGA, but it's too late. It already exists. You are right. Yeah. And we also looked into meta GGAs, and they have these strong extra branches. Yeah. Okay. So silicon, just as an example. And we also did sodium chloride at that stage, and later copper. And I must say, we completely depend on our quantum Monte Carlo friends here, because we need the reliable quantum Monte Carlo data, which is not what we produce. We only produce the inversion and the analysis. So it's a collaboration that really relies on 2 feet. Okay, so once you have this exchange correlation potential, then you can answer questions that people had over years. For example, how much of the so-called bandgap error in Kohn-Sham is due to the very fact that we use an auxiliary system, and how much is due to the fact that we do an approximation, for example, a local density approximation. Because now we have the in principle exact Kohn-Sham potential. So this is what we call here AFQMC. It's the result of the inversion for silicon and sodium chloride, direct gap at gamma, and the indirect gap for silicon. This is the experimental value, of course, with some error bar, but it gives you an indication. And you can see, for example, if you take the direct gap in silicon or the direct gap in sodium chloride, let's take this one, you have a huge error that is due to the Kohn-Sham itself, and a sort of minor additional error that is due to the functionals. And by the way, our results are very close to the PBE results. The PBE, and this seems to confirm that PBE is a really good functional, which does not mean that it can correct the so-called bandgap problem, because it's inherent in what you are doing. It has nothing to do with exchange correlation. Huh? Okay, and this, of course, I mean, this is not the complete surprise. There was a lot of earlier work, which I have to acknowledge here, of people who with different approximations looked into this problem and also came to this conclusion, but I think it's the first work where this is numerically very, very reliable, thanks to the auxiliary field quantum Monte Carlo. Okay, so this is one of the informations you can get as a byproduct of this project. So now we have this reliable benchmark, and now we can see how far we can get, for example, by building perturbative functionals. Perturbative, not in the interaction, but in the potential. Okay, so let's just do it. So we just go to first order. This is the first order expansion of VXC around some homogeneous density using this exchange correlation kernel. So what we have here is, again, silicon. This is a path in the silicon crystal between different atoms. Okay, you have the gray line, which is a Monte Carlo error bar. So what we look at here is the error in percentage error in the density. So the Monte Carlo error bar, this is because this line is not infinitely fine, statistic error bar. We have the density, which is indicated on the right side, and this actually answers you, Andy, because it's a very inhomogeneous density, as you can see. That is the calculated density of silicon. And then the first thing we do, we just take the average density of the system, the mean density, and we use this as our zero starting point. And if we plug this, we get, of course, a constant exchange correlation potential. And with this, we can calculate in a Kohn-Sham way the Kohn-Sham result, charge density. And this is the green line here. This is the error that you get when you do this. And you see, you get, of course, huge errors up to 75% if you just do the zero order. You just take the homogeneous. So the exchange, the fact that the density is not homogeneous when you calculate your exchange correlation potential is very important. Now we add the first order. And the first order, this linear expansion around the mean density gives you the red error. And as you can see, there is a huge reduction of the error, really a huge reduction. So this is actually really much better. And this tells you that this simple, straightforward perturbation theory in the potential for materials like silicon, which are not super inhomogeneous, is already very promising. Actually, we were quite shocked by this. Okay, then shock went away because we looked at sodium chloride, which is more inhomogeneous, and also copper. And in sodium chloride and copper, we did the same thing. So the green line is what you get if you start out with a homogeneous density. Of course, it's terrible. And the red line is what you get with the first order. So what you see is you just turn the error around. So you do correct, but you overcorrect. And this is, of course, because now we are so inhomogeneous that perturbation theory starts to have problems. You know this. It starts to fluctuate, right, when the perturbation is too strong. I was still quite pleased to see that the correction goes in the good direction, and in some places it actually does correct. Okay, but it's certainly.
This is pseudo-potential calculation. Sometimes the density seems to go to zero.
Yes, yes, yes. I should have said this. Yeah, yeah. It's a pseudo-potential. Exactly. It's an additional problem. And if you look at our errors, they're actually exactly largest on the atoms. Exactly. Exactly. So this also as a side remark, when you look at these plots I have shown before with the extra branches and so on, the extra branches typically sit on the atom, right? So there are two things that you can conclude from this. One is in this specific material, you can ask yourself, in this specific material, will I have an extra branch? And the answer is maybe not. Maybe it comes from the pseudopotential. But as a functional is a universal functional. So if you create a material with this kind of environment, there should be the extra branch, right? So as a functional, it's still valid information. You can just ask yourself, will I ever have such a pathological material, right? Exactly. Very good. Okay. Okay, so of course, this is even more inhomogeneous than silicon. So in simple semiconductors, we could probably get away with this. So, wow. But now we want to do better. Okay, so now you can, let me speed up a little bit. You can improve, of course, perturbation theory. You have a huge mathematics literature on perturbation theory, right? For example, when you do first order perturbation theory, if you take your derivative, instead of taking it at your zero order point, at some suitable intermediate point, you will get a better result. You could even get the exact result if you have the best point, okay? And of course, we can only take a point that is itself homogeneous because we only know fxc in this derivative in a homogeneous system, but we can still make a point, in this case, a sort of average between your zero order starting point and the density that you plug in here. You can still do this, and we can get better results. You can see this if you just look at the homogeneous electron gas. So this is VXC. as a function of the homogeneous density as you get it out of quantum Monte Carlo. Okay, and we expand around some point, for example, this point or this point or this point. Yeah, and then you can see that the first order, so the zero order is this point, it's a constant. The first order is the green curve, and around the point it's quite good, and then you go away, and of course it's much worse. The second order, and you can see a convergence problem, is getting better, but then at some stage it might deviate, like you know from an asymptotic convergence. But if you take this midpoint that we did, then you get actually much, much better results, right? So this is certainly an improvement. But the problem is when you do this order by order, even improved, you lose something, and this is the correct limit for a homogeneous system, and this is really a pity. So we get results of if our real system would be homogeneous, and we would expand around a density that is not the density of this homogeneous system, but another homogeneous density because we are stupid, okay? We would not get the correct result. We would get a result of sort of this quality. And it's really a pity. And so here is something else that you can learn from density functional people. Always impose exact conditions. This is really, really, really helpful. We don't do this enough in Green's functions, I think. So here the exact condition would be, for a homogeneous system, we know everything, we want the correct result. So we use it as an exact constraint. And the way we do this is what we call a connector theory. So this is one particular realization of what we call connector theory. It's a more general approach that links model systems to real systems. So what we would say is we sort of exactify the LDA. We say that our exchange correlation potential in a given point equals the exchange correlation potential of a homogeneous system with a density that we do not know, but we would like to know. So it's not the local density, that's an approximation. But there exists a homogeneous density in most cases that would make this equation exact. Okay, depends on the domain of your functional. Okay, then you could invert and find this, but of course you don't know the exact result. So you don't know this exact, what we call connector. But then we have a strategy to find it. And the way we do this, roughly speaking, is we do an approximation. For example, linear expansion, okay? Our linear response approximation. We do this approximation on the model. We do it on the real system where you have just seen that we can do it. From this, we can get this connector. So we do the approximation, we get the approximate connector, and then we use this approximate connector in the exact expression. Okay, so it's a shifting of the problem. But as always, when you shift the thing in a clever way, you get a lot of error cancellation. And this is what we get here. Because we do the same approximation on the model and on the real system, we have a lot of error cancellation on this connector. And this is the way that we have to impose the exact result of the homogeneous electron gas. And if you look now at the results, so on the upper panel, you have silicon, on the lower panel, you have the sodium chloride. This red line, which has a HEG, homogeneous electron gas appendix here, because it imposes this condition, has a very, very, very small error in silicon. You see, it's really the best result we can obtain. It's better than the PBE, for example. And in the sodium chloride, I would say it has a lot of dignity, okay? It's also similar to the PBE, not quite as good, but it has a lot of dignity. And this is really a very simple and, for us, very important, absolutely systematic approach. It's not like fitting to molecules. It's not like empirical parameters. It's really like knowledge from perturbation theory and imposing an exact constraint. Okay, and you might want to look at this scatter plots of the potential. We have a lot of things here. Don't worry. But you might remember in silicon we had this extra branch going here in the quantum Monte Carlo, which the PBE had on the wrong side. So now we have it on the right side here. So that is very reassuring. But we don't have this extra branch, a correct description in the sodium chloride. Okay, sodium chloride on the atoms, on our pseudo atoms, is still very tough. And since we talked about this meta GGA things, they get this extra branch in an exaggerated way. So these are sort of overview of errors. The only thing that you should look at here is the thing that we are systematic. So we go, this is maximum error on the density. We go from our initial like linear expansions to something that is really very much better than everything we can do on the way. And this is what we want, systematic way to get it. These are mean errors, and we are on a level which the best available density functional today have. So we are quite satisfied because this was meant to be really a showcase. We have not yet optimized our functional. We can do a lot of things. We can introduce parameters, impose other exact constraints, okay? This is just what we get from a boom, straightforward way to do things. Okay, so should I maybe, can I take another 5 minutes or? Yeah, just to tell you that we are not limited to density functionals. I think this is important. So as I said, the density is a descriptor, also for historic reasons, right? I don't know whether you ever have thought about why the hell we use the charge density to describe our system. If you want to discuss this, we can do it later. It's not so obvious. The most natural descriptor is actually the external potential. It's natural because it's the thing we know. The density we don't know, huh? We have to get it first. We don't need any Kohn-Sham system if we have the external potential as a descriptor. And if you have a simple relation between your observable and the external potential, you can hope to invert this relation and to do inverse design. So to say, I want this charge density, where do I have to put my atoms, right? That's the dream of everyone. So I think the potential, functionals of the potential is very important. So the first work that Mohammed has been doing was not a functional of the external potential, but of the total Kohn-Sham potential to work in a non-interacting way. And let me just sketch that it goes in the same way. So now we expand. So now our observable we are interested in is the charge density. It's no longer a potential, it's a charge density. And we expand the charge density in terms of the total potential, okay? This is also a linear expansion, but we have reverted the role of the two things. It's a little bit confusing. Charge density is the observable. The potential is the descriptor here. And the first derivative is, of course, just the Lindhardt function. Okay, so we know. Excuse me?
The meaning of the tilde.
Okay, the meaning of the tilde is because you might remember that earlier I said we can take the derivative in a different point. So the tilde indicates that we can play with this point where we take the derivative, yeah. We will just use the whole machinery that we have learned from the exchange correlation potential to do the same here. Okay, so we have the zero order term, we use the connector, we use the whole machinery. And to give you an impression what we get, so if you have your zero order, just a mean potential, okay, which is up here, okay, you get, of course, a homogeneous density, which is crap. This is solid helium. In this case, we decided to take a very inhomogeneous system from the very start. So this is solid helium. We use, again, the homogeneous electron gas as a model, so it's really terrible. And here are the atoms, and you have, of course, high density here on the atoms, okay? So we calculate the density functional theory. So this sets our total Kohn-Sham potential, okay? High density on the atoms, very inhomogeneous. Zero order would be just a homogeneous density, completely crap. And the first order is this dot dashed lines. Now you can be sort of happy because, of course, your first order understands where the atoms are. You get a high density on the atoms. And you can be completely depressed because what does linear response do? Of course, it overshoots. And where the density should be low, it's negative. That is terrible. You don't want negative. This is completely unphysical, right? Another possibility is to do the equivalent of the local density approximation, namely the local potential approximation, which is nothing else but Thomas Fermi. So you calculate the local density from the local potential, okay? And this is the result. It actually looks much better. This is the local potential approximation. So you see, instead of having your Kohn-Sham code and running this for a big material, you just take this simple formula, and this is the result. So the reference density again from DFT is in black. And what you get from the local potential approximation is this green curve. And I must say that in view of the simplicity here, this is not that bad. Of course, it's not good enough, but it gives you a lot of information. So suppose you have a very complicated interface and so on, maybe you want to look into this. Okay.
Sorry, just a minute, Brian. The local potential approximation is an approximation to the pi-0 that is in a previous.
Yes and no, in the sense that you can see it either as a approximation here, making it completely local, but I think it's better to just say, now I change my zero order, okay? And instead of taking the average potential here, I take the local potential. Yeah.
But there was no calculation. Well, I guess my question was there a calculation of the Linford function in the helium thing that goes?
Previously, yes, when I said linear response.
Right, but in the helium thing that goes.
So this one has linear response with the negative densities, but now we start again and we change the zero order, and this is much better. And no linear response yet. Okay.
My other question is, it looks like one curve is systematically below the other. Did I have the same number of electrons?
No. Very good. Exactly. We don't get the same number of electrons. And actually, it's different from what you would think, because you would think that we don't have enough electrons, right? Because you see this. But actually, we have too much electrons, because in 3D, this low density region here is very extended. And there is where the electrons sit. So we have actually too many electrons. Yeah. Okay. And then we go with the machinery. So to make it short, we expand around this local potential approximation. We take a better derivative point and we use the connector. And then we get this result. So reference DFT in black. The local potential approximation, which is the analog of the LDA in green. And then this latest result with the black dots. Okay, so we have a lot of improvement here. We have an improvement on the atoms. It's not perfect. You can distinguish the curves. But again, it's a very simple formula. And we think that is a quite promising starting point. Because at the end, we are, of course, interested in the interacting system. Okay, so we are now extending this to get a functional of the external potential, which would allow us to do everything without ever passing through Kunsham. Just relying on what the Monte Carlo people have given us in the homogeneous electron gas, namely interacting response functions. Okay. For further aspects, let me just mention this, and I come to my conclusion. We always look at these descriptors and for the auxiliary potentials as functionals of their respective descriptor. This is not necessary. Okay. We should not say, for example, the self-energy is a functional of the one-body Green's function. We can express it as a functional of the one-body Green's function, but we can equally express it as a functional of the density. And this allows us to mix the different functionals. For example, diagrammatically, this is the exact self-energy, where you have derivatives of the self-energy with respect to the Green's function and the Green's function with respect to some potential. Well, this sort of chain rule here, which is written here, you can equally insert the density. Then you get more compact objects in your diagrammatic expansion, which you can more easily import from model systems. So that's for us also a promising way to go. Okay. So to summarize, we are searching for approximate functionals of relatively simple descriptors, and we allow ourselves to have a wide variety. We are not bound to the traditional ways of using either density or Green's function functionals. Linear expansions and beyond, and especially using this connector way to impose exact constraints is very promising, we think. And they all fit into this work once, store and share philosophy that I would really like to advocate. I think that we are at a point where we have to be more ecological and more collaborative. And thank you for your attention.
Yeah, I could. So it was back when you were showing the densities for the different methods, it was specifically about one of the plots. There was the red dotted line, which I think was the first order, and there was a yellow dotted line, which I wasn't sure what.
Okay, I didn't talk about all the lines because it was a little bit. Do you mean this one?
Yeah.
Yeah,
Well,
maybe.
it might have been a little before this still.
Uh-huh. Not this.
This
This.
yellow line here.
Okay, so this one, actually, I don't remember, but it could be another flavor of connector. Yeah, we have different flavors here, and I didn't want to swamp you out with all the different things we have, right? It was a sort of less systematic one. Yeah, it's not the LDA. Yeah. So the red one is the one, okay, we want to avoid to use for every material the best one, okay? This is cheating. So the red one is the one that I consider to be the most systematic.
Thanks.
So Lucia, you advocated the importance of using exact constraints to help with constructing functions. Can you sort of exemplify that? What exact constraints would you recommend?
That's a super good question. So, for example, in the last part, Andy already pointed out that we seem to not to have the good electron number, and this is true. And even at the end, with our best results, we still don't have the good electron number. So we will definitely use this as an exact constraint. Okay. The simplest way to do it is to analyze where we have the worst approximation in our series, and there put a parameter and fix this to the exact constraint. So electron number is super important. And then it depends on the framework where you are. In the density functional framework, people have a lot of exact constraints, zero force theorem, harmonic potential theorem, and so on and so on. And for example, the most successful functional that was recently developed, the scan functional of John Perdue, has 17 exact constraints built in. Okay, so they have a lot of exact constraints. There is one that is very interesting and that us Green's function people, I think, should use, and it's the piecewise linearity. So the piecewise linearity means that when you allow for fractional electron number and you vary the total energy, it should be piecewise linear. This is linked to Koopman's theorem, and it has turned out to be extremely powerful for the DFT people. For example, those who tune the hybrid functionals like Leo Kronig. And of course, we Green's functions people also are not respecting this piecewise linearity. They're not piecewise linear, okay? You start with Hartree-Fock, completely off, okay? So this is something that we could import, I think. Now, why is this so powerful? This, I don't know. And I have been harassing all these people who do the piecewise linearity to explain me why it's so powerful. There's no answer yet, okay? So globally speaking, only the exact result will fulfill all the exact constraints. This is clear. If you have all the exact constraints fulfilled, you have the exact result. And the art of knowing which ones you should pick first. This is something that is also, to me, a very interesting subject of discussion. And I don't have a general answer. I only have experience, but not deep understanding. Mathieu has a question.
Hold it down. Oh, it's not work. You keep using the mean density and the mean potential, and it's always 1 + 2/2. In principle, there's probably a much better recipe which tells you exactly, even for any arbitrary nonlinear curve, which fraction of each point you should be using in a susceptibility.
Exactly.
And there you can probably also get some kind of universal variable fractions. It feels like it's going towards some gradient, but it's also fully non-local. Do you have some input for there, or are you
Yeah.
going to do something more?
Yeah, it's also a
fancy?
very important point. So there are two problems here, okay? The first one is if you had a function, you know that if you put your derivative in the midpoint, you get the exact second order, which is nice because you're in first order. Now, if you want also the higher orders, then you have to put it somewhere else, and then it becomes less universal, okay? The second problem is, here we don't have a function, we have a functional. So suppose you choose the midpoint between your zero order density distribution and your true density distribution, okay? This midpoint, this average, will itself be non-homogeneous. And then you don't know how to calculate this derivative because we get the derivatives from the model, from the homogeneous electron gas. No one has calculated for us the derivative in a non-homogeneous system. So we must choose a midpoint that is itself homogeneous. And actually what we do is a sort of double connector approach. So we choose the best homogeneous electron gas for that derivative. You can write it down. And this best midpoint contains the second derivative, the GXC. Okay, so if we had the GXC, we could have a much better intermediate point, but we don't have it. So maybe at CCQ, someone will give us the second derivative in the homogeneous electron gas, then we will use it. Yeah, that would be great. That's actually one of the points where I'm really sort of sorry for the fact that we're missing this ingredient. I really hope that this can be also motivation for people to give it to us. In the meanwhile, I think since we know that here we have a weak point, that is why I would put a parameter to fix an exact constraint. No, in this derivative point. I think we can actually learn again much more from the mathematicians who have worked on perturbation theory, and we have to look more into discussion with mathematicians to see what we can do better here. This was a very, when I said that in the old days, people already looked into these expansions. No, this was Kohn himself, Walter Kohn and Gunnarsson and so on, but they didn't sort of see it in the way of a Taylor expansion. And so they said, oh, where shall we take the derivative? Maybe we take the density. If I have a density here, the density here, I take the density in the middle, okay? And this gave terrible results because you can have a molecule density in the middle is zero and the whole thing makes boom. And this is one of the reasons why this approach was actually abandoned, right? But if you do it in this systematic perturbation theory, like spirit, then you realize what you should do. And then the question is only, can we do it?
You're taking the average of the densities, not the density of the average point.
Exactly, that's very important. Because this is what perturbation theory of a multivariable function tells you to do.
Could I ask you a
This is
question?
something that was not clear in the past.
Just go ahead, Cyrus.
Yeah. So I have a question again on this fitting of the exact functional, or kind of the generation of the exact functional from the QMC.
Mm-hmm.
I guess what you're saying is that there, even the exact functional of the density does not give you these other observables exactly, like the band gap. So if you were to generalize it to allow kind of the like a hybrid like term in your Kohn-Sham equation, then can you get the exact do you get the correct band gap, for example, with the exact?
Yes. So actually, it's something I'm working on, is the fact that for every observable you're interested in, you can build a convenient auxiliary system that would give you this observable exactly in principle. If you want more than one observable, then you would have, of course, a more complicated auxiliary system. And the best example is the Green's function as a descriptor, right? So we have a complicated auxiliary system here because we have the self-energy. And we know that if we had the exact self-energy, we would get the exact one-body Green's function, and therefore, for example, the exact electron addition and removal gap. Now you ask, could we make an auxiliary system that is a little less complicated than that one? For example, suppress the frequency dependence of our potential object and still get the good band gap, right?
Yeah.
So,
right.
And the answer is probably yes. Yes, if you just want the band gap. If you want the whole spectral function, no. Okay. But then even for the band gap, if you think that your band gap is not a quasi-particle gap, but something in a really strongly correlated system, this has to be seen. I'm not so sure. Okay. So not so sure in principle and not so sure in practice, because it could be that then your non-local static object is highly pathological. So it could exist, but be highly pathological. So it would not be a good way to go. But yes, I think, so I'm interested in this, designing auxiliary systems for different kind of observables, which we have not yet been looking into. I think that's a promising way to go, because then you have these auxiliary systems with the auxiliary potentials that you can maybe get from a model.
Yeah, that's yeah. Thanks for the answer. That
and let me just add that, of course, the generalized Kohn-Sham equations, which is the Kohn-Sham equations with a static but non-local exchange correlation potential, exactly goes in this direction. Hybrid functionals are one approximation to generalized Kohn-Sham, and we all know that they give much better band gaps than the straightforward Kohn-Sham. Not because they are better approximation, because it's generalized Kohn-Sham. It's a different auxiliary system. This is sometimes mixed up.
Yeah, it would be really interesting to kind of have the same theoretical basis that you're giving for the normal Kohn-Sham system, where you're saying that there's no point in searching for a better functional to get the band gap, because it that functional does not do it for the hybrids. So is it legitimate to search for a hybrid scheme that gives you the correct band gap? You know, does the exact hybrid in quotes actually give you the correct band gap? You know, taken from QMC like you did with the
Yeah. So there is work on this. In particular, let me mention Wei-Tao Yang, who has also recently worked on this. And then there is a quite bigger paper with also John Perdue. So people are thinking about all this. And as I said, I think if it's just a number, just a band gap, then you probably have enough freedom. But if you want more than that, good band structure and so on, then we still have to look into it. Yeah.
Thanks.
Yeah, so it's not just hybrid functionals. The hybrid functionals are one approximation of generalized Kohn-Sham. Yeah, and by the way, if you take the hybrid functional, so if you start with the total energy as a functional of these orbitals, you can do two things. Either you do your variation with respect to the density matrix, then you get the generalized Kohn-Sham equation with its nicely large band gaps, or you do the variation with respect to the density, then you get an ordinary Kohn-Sham potential, and the band gap is again small. So that also tells you how much is due to the Kohn-Sham local potential itself.
Just as a comment to that, so hybrids, technically, I think of them more as an approximation to the non-local self-energy, not really to the exchange correlation. Right, so if anything, it would be sort of an exchange correlation approximation to sigma in the static limit, which is why they behave better.
So you can see it both ways, actually. I agree with you because I come from Green's function, so I love to see everything as an approximation to what I'm doing. But it's one way to see it, and then you see immediately that you suppress the frequency dependence, so there must be a problem on the spectral functions and so on, right? But the other way, as I said, is generalized Kohn-Sham. This is a theory that exists per se and has a lot of theorems, and fine. Yeah.